Hello dear students. We had done several examples of groups. So let us continue with some more examples, as the first unit is basically deals with groups and their examples of groups. Okay, so there are several standard groups which we need to study. So let us try another one, this exercise which I had told you, the set Q plus of positive rational numbers is a group under multiplication. Okay, so how do you discuss this? So in fact the set Q difference singleton 0, that is the set of non-zero rational numbers, that is also a group under multiplication. We will also see. Okay, so let A comma B belongs to Q plus, then A into B. So if I take the product of two positive rational numbers, then I will get a rational number. Okay, so this closure property is satisfied, right? Then we know multiplication of rational numbers is associative. Yeah, multiplication of rational numbers is associative. Okay, so A dot B dot C. So here please note that the operation here, instead of denoting by star, we can denote by dot. Okay, because this represents multiplication. So A dot B dot C is equal to A dot B dot C for all A, B, C inside Q plus. Okay, the associative property is satisfied. Next we want to consider the existence of identity element. Okay, so what will be the identity element? As we know here, which rational number multiplied with any other rational number gives the rational number itself. Means which rational number, say E multiplied with A gives you A itself. So that answer is actually 1. If we multiply 1 with any other number, and then we get that number itself. Okay, so we know that 1 is a positive rational number, so we have 1 belongs to Q plus, and 1 into A equal to A into 1 for all A inside Q plus. Okay, if we multiply any rational number with 1, we get the number itself. Okay, so 1 is the identity in Q plus. Okay, next we have to think about the existence of inverse element. So let A belongs to Q plus, be any element. Okay, so then, since it is a positive rational number, so A is non-zero. Okay, thus, so since A is non-zero, 1 by A is also a rational number, and it's a positive rational number. Okay, since A is non-zero, so we can always take the reciprocal. 1 by A belongs to Q plus, and A into 1 by A, this is equal to 1 by A into A. So 1 by A is the inverse of A. Okay, in Q plus. Okay, so we have verified all properties. This is the closure property, associative property, this is the existence of inverse, and this is the existence of identity, and this is the existence of inverse. Any element in Q plus will have its inverse. Okay, so thus the set Q plus is a group with respect to multiplication. Okay, so if your question is show that the set of Q plus of positive rational numbers is a commutative group or abelian group under multiplication, just you need to add this extra property that we know multiplication of rational numbers is commutative. Okay, so just we can add that part. So the case for non-zero rationals is exactly similar. So I give you as a task to verify that the set Q difference singleton 0 of non-zero rational numbers. Non-zero rational numbers is a group under multiplication. Group under multiplication. Okay. So similar to that, there is another one, the set R difference singleton 0 of non-zero real numbers. So last day also I think I gave you this exercise, so you can try it. The proof is exactly similar to this one. Okay, whatever it is, just the writing is little bit different. Here instead of AB belongs to Q plus, you will write AB belongs to R minus singleton 0. Okay, so everything else is same. So the set R minus singleton 0 of non-zero real numbers is a group under multiplication. Multiplication. So let us try another exercise. Suppose your question is something like this: is the set n of natural numbers a group under with respect to multiplication? Okay, so this type of one mark questions can come in exams, so you just have to justify your answer. Okay, so is the set n of natural numbers a group with respect to multiplication? So obviously, so you see here many of the properties are satisfied. If I take two natural numbers, then their product is actually natural number. Okay, then it satisfies the associative property. Okay, multiplication of any numbers is always associative. This is satisfied, this is satisfied. Identity is also satisfied. 1 into a equal to a into 1. Okay, for all a, right? So this is also satisfied. What is not satisfied is the fourth property, existence of multiplicative identity. Okay, so what is not satisfied? The multiplicative identity property. Okay, so n is not a group with respect to multiplication. Okay. Multiplication as say we start with an element which belongs to n but doesn't have multiplicative identity. 2 belongs to n, has doesn't have inverse. Okay, multiplicative inverse. Okay, so what is the possible multiplicative inverse of 2? It is half. Okay, so half doesn't belong to natural number. As half doesn't belong to natural numbers. Okay, half is the possible multiplicative inverse of 2. No, half into 2 is only 1, right? So but the element half is not a natural number. Okay, so n is not a group with respect to multiplication. So similarly, z is not a group with respect to multiplication. Okay, these things also you can verify. Z is not a group with respect to multiplication. Yeah, so these are just one mark questions. Can you try this? Is Z a group with respect to division? With respect to division, right? The answer is no. Why? Because here the operation itself cannot be defined for many means pair of elements, as division by 0 is not defined. Okay, division by 0 is not possible or not defined. Okay, so you cannot have something like 2 divide 0. Okay, this is not allowed, right? So this is not a group. The set of integers with respect to division is not a group. Okay, similarly the set of integers with respect to the subtraction is not a group. Okay, Z with respect to subtraction is not a group. Is not a group, right? It doesn't satisfy many of the properties, right? Say associative property, 1 minus 2 minus 3. What is that? 1 minus 1, right? So that is actually 2. But 1 minus 2 minus 3, this is actually equal to minus 1 minus 3, so that is minus 4. So they are unequal, so therefore Z is not associative. Associative with respect to subtraction. Subtraction, right? Okay, similarly R is also not a group with respect to subtraction because of the same reason. It doesn't satisfy associative property. It doesn't satisfy the existence of 0 also, because you see 1 minus 0, this is equal to 1, but 0 minus 1, this is equal to minus 1, so it's not satisfying that property. No? A plus 0 equal to A equal to 0 plus A, this should be satisfied. Okay, so subtraction doesn't satisfy this particular property, so it's not a group with respect to subtraction, right? So let us see some more examples. Yeah, so say the set of irrational numbers with respect to multiplication okay, is not a group, right? Set of irrational numbers with respect to multiplication is not a group. Why? The justification is very simple. Say you have root 2 belongs to this set, right? The set of irrational number, let's say I. Okay, I is the set of irrational numbers. Root 2 belongs to I, but root 2 multiplied with itself, that is equal to 2, it is not an irrational number. Okay, so it's not closed. I is not closed with respect to multiplication. Okay, I is not closed, so we cannot define the operation itself here. I is not closed with respect to multiplication, right? So product of two irrational numbers is not guaranteed to be irrational, it may be rational also. Okay, so that is the problem that crops up with irrational numbers. Okay, so some other examples let us see in terms of matrices. So the set so the set say A or M, okay, M2 equal to the set of matrices, okay, A, B, C, D, okay, such that A, B, C, D belongs to R. this of 2 by 2 matrices. Okay, 2 by 2 matrices is a group with respect to addition. Okay, this is a group with respect to addition. So how do you define this operation? The operation is defined as this. Okay, for so let us take one element x. For x equal to a, b, c, d, y equal to say a, b, c, d, say e, f, g, h in M2, x plus y, how do you define this? We define it as a plus e. The corresponding elements are added. Okay, so in your higher secondary you have already done this. Say plus g, d plus h. Okay, so this is also a matrix. No? Sum of two by two matrices is also a 2 by 2 matrix. Okay, by definition of the sum. Okay, so closure property we have verified. Okay, then next comes the associative property. So we can write, we know matrix addition is associative. Okay, by properties of matrices we know this. Matrix addition is associative. Okay, and we'll prove the general case also where we can do it as required. Okay, so what can be the identity element here? Which element may work as the identity element? So you can just think a little bit that actually if identity element means x plus, suppose y is the identity, then x plus y has to be x only. So what should be the elements here? Obviously this has to be 0. So a plus 0 will give us a only, b plus 0 will give us b, c plus 0 will give us c, d plus 0 will give us d. Okay, so 0 is the identity element, the null matrix. Okay, so we have say O equal to or O2 equal to this null matrix 0 0 0 0 all 0. Okay, belongs to this is a 2 by 2 matrix. Okay, belongs to M2, and any matrix A, B, C, D added with 0 0 0 0 is always equal to A plus 0, B plus 0, C plus 0, and D plus 0. Okay, so this is same as A, B, C, D, right? And the other way also it is true. It is also equal to 0 0 0 0 plus A, B, C, D. Okay, for any A, B, C, D inside M2. Okay, you take any element from M2, this is always satisfied. Okay, A, B, C, D added with the null matrix will give you the matrix itself. Okay, so O2 is the additive identity, or just let us write identity in M2. Okay, next we have to think about the inverse. Okay, inverse of each element. Now for x equal to A, B, C, D inside M2 we have, so if we just make this elements negative, okay, means if we change their signs, okay, this element, this matrix Y, this is also an element inside M2, and it satisfies x plus y equal to A, B, C, D plus minus A, minus B, minus C, minus D. Okay, so what do you get? A minus A, this is 0, B minus B, this is 0, C minus C, this is also 0, D minus D, this is also 0, which is equal to O2. Okay, which is also equal to y plus x, we can verify, right? So y is the inverse of x. Okay, so we have verified all properties, right? So it's closed with respect to addition. It has associative property, it has identity, every element has an inverse. So this is a group. Okay, so this M2 is a group with respect to addition. Okay, with respect to addition, right? So let us try the general case. Show that the set, say Mn of n by n matrices, okay, or say m by n matrices. Let us take a general one of m by n matrices with real entries, okay, is a group with respect to addition, okay, with respect to matrix addition. Okay, so the operation that we define here is matrix addition. Okay, addition of matrix, how we add it. Okay, so let us see how we can formally prove it. Okay, so formally we should write it this way. So what is n by n? This is the collection of all m by n matrices. So in general we denote it as aij m by n. Okay, such that aij belongs to R. Aij belongs to R, where I comma j, they varies from 1 to up to, I have to write it in two parts. I varies from 1 to up to m, I goes from 1 to up to m, and j goes from 1 to up to n. Okay, this is the general notation of matrix, right? You have done in higher secondary aij notation, aij m by n. Okay, so let a equal to aij m by n, comma b equal to, say, bij m by n, belong to m by n, be any elements. Okay, be any elements. Then how do you define a plus b? A plus b is defined as the matrix Cij m by n, where this Cij is what? Cij is nothing but aij plus bij. Okay, this is the definition of matrix addition. So by definition itself, a plus b is a member of m by n only, because it's a, we have defined this to be an m by n matrix only. Okay, Cij equal to aij plus bij. This also belongs to real numbers, because the set of real numbers itself is closed with respect to addition. Okay, right? So these entries of a plus b, they belong to reals. Okay, so that is why a plus b is an element inside m by n. Okay, next I have to verify the associative property. Okay, so let a equal to aij m by n, comma b equal to bij m by n, comma c equal to cij m by n. Okay, be any elements. Okay, we take three elements in m by n. Okay, so what I have to show? I have to show that a plus b plus c. Okay, this is same as a plus b plus c. Okay, so a plus b plus c is what? It is the matrix where a and b are first added. So it is aij plus bij in matrix notation. This is m by n plus this is cij m by n. Okay, so I can write this as, in matrix notation, it is again aij plus bij plus cij. Okay, the elements are added component wise. Okay, and then since these are real numbers, aij, bij, cij, they are real numbers, so I can write it as aij plus bij plus cij. Okay, so I can separate it this way, m by n. So this can be written as, by definition, it's aij m by n plus this is bij plus cij m by n. Okay, so this is nothing but a plus, and this is b plus c. Okay, so the matrix addition is associative. Okay, so matrix addition is associative. Addition is associative. Okay, right. Next, we have to find identity element. Okay, so let O equal to say 0 m by n. Okay, or say Oij Oij m by n, where each Oij is actually 0. Okay, Oij equal to 0 for all I comma j, right? That is be the null matrix. Okay, null matrix. Then the null matrix in m by n. Okay, this is a null matrix of order m by n. Then a plus 0 will be always equal to a equal to 0 plus a for all a inside m by n. Okay, so therefore 0 is the identity. Okay, 0 is the identity, right? Next is we have to find out the inverse of each element. Okay, for a equal to aij m by n in m by n, we have b equal to minus aij m by n. Okay, this is also an element inside n by n, and a plus b is equal to what? Aij m by n plus minus aij, means I have taken a matrix whose all elements are negative, means opposite of sign of that of a. Okay, so if I add these two, I will be getting aij plus minus of aij. Okay, m by n, and that is nothing but 0 m by n. Okay, so that is the null matrix, right? So this is also equal to b plus a. Okay, so this is so minus aij m by n is the additive inverse, or is the inverse of aij m by n in m by n. Okay, so every element has got an inverse. So therefore the set m by n is a group with respect to addition. Okay, with respect to matrix addition, right? So not only that, it's also a abelian group. Okay, it's an abelian group. You can easily verify a plus b, the sum of two matrices is always commutative. A plus b is always same as b plus a. Okay, so this also you can verify, it's an abelian group. Okay. So if in question is your question is something like whether this is an abelian group or not, your answer is yes, it's an abelian group. Okay, so another group which we will discuss, I'll just give the heading, you can try to prove it. The set GL and R. So this is actually called generalized linear group. So till now we have seen groups of matrices with respect to addition. Now we will see with respect to multiplication. Okay, so this is called generalized, or the general linear group. Okay, general linear group. Okay, what is it? It's on the set of n by n matrices. Okay, G, L and R. The set G, L, N, R. Okay, G, L, N, R of what is this set? It is the set of n by n matrices. Okay, matrices over R. The set of this of n by n matrices over R with n by n, this is non-singular matrices. Okay, means determinant is non-zero, non-singular. Okay. This, right? So the set GLNR of n by n non-singular matrices over R is a group with respect to matrix multiplication. Matrix multiplication. Okay, so you try to justify this. We will discuss in our next lecture. Okay, GLNR, the set of n by n non-singular matrices. Okay, non-singular means determinant of A is non-zero. Okay, so if we take the collection of all such non-singular matrices, then it forms a group with respect to multiplication. Okay, if we do not take non-singular matrices, then it's not going to be a group. Okay, we will see examples where this happens. Okay, so this is an exercise for you. You try to think. In the next lecture, we'll discuss about this. Right? Thank you.